try to show that to find a distribution of this quantity. Okay, this quantity. So the idea here is that you have the random sample from some distribution mu, right? And variance sigma square, right? And now you just take the sample, right? The sample. You just take the sample uh, variance, right? Sample variance Sn square. And now we need to find the convergence of this whole quantity, right? This whole quantity. So what I'm sorry, so find the distribution of this whole quantity, right? Whole quantity. What distribution here? So if we just look at it with direct in a very direct way, and it's a bit tricky, right? Because now thing is not so kind of clear. I mean, in a sense, like which one is which one, right? Now you have something with a sample in the numerator and something with the denominator, right? So for this kind of thing, basically, like we need to we need to be a little bit smart by twist around a little bit by implementing something in the middle. So you can see the connection of Sn and sigma square, right? So previously, so if you recall in the previous class, right, Sn square it converges to sigma square in a property, right? Probability. So previous right class, right? In example 935, right? So now you try to make use this property, okay, to to um, to basically like you need to make an easier transition, right, from Sn to sigma square here. So in order to do that, basically like one trick people they also do is that often they do like, so instead of looking at this directly, right? Maybe I come here my test t, okay. So my t here, I can see it. Oh, actually, I can just divide by sigma, right? And times sigma, right? So this is a trick we do. Right? So I just time sigma and divide by sigma. Okay, I didn't do anything, just time and divide, right? And then you can see that this guy, right? I can rewrite this fashion, right? What n bar, right? Subtract the mu. Remember, one n bar is just the mean of y1 to yn, right? By sigma square by square root n, and time 1 by Sm plus sigma, right? So nothing new here, right? Nothing new here. So you can see that the first term, right? The first term is from a central limit theorem. We did learn that this guy conversion to a z, right? Conversion to a z from a central limit theorem. So know that slide. Note that the central limit theorem, right, tells us the yn here. Sigma by square root n conversion to a not more 0, 1, right? So this is what we have a central limit theorem. And from example from 935, right? Example, we have Sn square convergence in probability, right? Probability to sigma squared, right? So which means Sn by sigma square here, right? conversion in probability to 1, right? To 1, right? And you can use the continuous map beam theorem. You can also see that, which is Sn by sigma conversion in probability to 1, right? So which means now you have one conversion in distribution, right? To distribution, one conversion in this probability to 1, but conversion in probability basically it's just nothing else than conversion. I mean, you can make it conversion to distribution, right? To 1, right? So which means like from a Slutsky, right? From Slutsky theorem. Slutsky, right? Slutsky theorem, right? We can have this guy, right? Divided by this guy, right? Conversion in distribution to normal 0, 1, okay? So you can see now you can improve this thing based on the probability we have, right? So in distribution, it conversion for n, large n, right? This quantity conversion in distribution to normal 0, 1, or the test statistic, right? T will conversion in distribution to normal 0, 1, right? Okay. So at least for a large sample, it's like that, right? Previously, we did show that for a small sample case, and it's actually this thing is a t distribution, right? But remember when for n go to infinity, and then the t and the will converge to the normal 0, 1, 2. Okay, so this is how you can apply these all the theorem and property to basically derive the distribution for the test square root n yn bar subtract mu by n. Okay, it ends. Question here. Okay. So now let's move on to sufficiency. Okay. So sufficiency is a very important concept. Okay. So basically, like it tells us actually what do you really need, right, to learn about the unknown parameter theta. So when you model, right, you model your random variable, you use a distribution, right? Say the normal, the exponential, or whatever. Okay. So your goal is that you want to estimate the unknown parameter in your model, right? Your model, and this means you need to collect data y into yn. Okay. And you do something, right? You do something with your data, and from that you can use that mixing nature, right? Which is statistics, right? To estimate the unknown theta. Okay. So the question now is that like what you really need to get from your y1 to yn. Okay. Do you need all of them? Or you just need like some kind of function of them, right? To learn about theta. Okay. And the thing will be become very powerful, you know, at the one dimension case, and then you don't see much benefit. Okay. But when you have like say multi, you may high dimension scenario, right? When your random variable maybe y1, the dimension maybe 1,000 by 1 or 10,000 by 1. Okay, y2 something like that. So say, you know, you think like people we observe the brain, right? Brain of a person, right? And if we divide by different voxel, right? You may can divide up to maybe 10,000 regions or 20,000 regions, right? So at that time, your data, it will record it by, each will be, say, you know, if you divide your brain in 10,000 voxels, and then basically like at each voxel, you have a signal, right? A signal for one person, you have like a signal in different voxel, right? The oxygen flow, whatever, right? Another time, like, say, basically you just have too much data, okay? The problem now, you have too much data because you have like, and then sometimes if you keep all of them and you process with all of them, it will be very noisy. It will be noisy, okay? So basically, like the idea is that like actually like which one I should keep it, right? Should I keep all of them? I just should keep a partial of them. I should keep maybe just um, a certain way, missing them, right? So this is the idea of sufficiency. Okay. So say like you have the whole data y1 to yn, but now if you have a statistic, okay, u equal to a function of y1 to yn, term g y1 to yn. Okay, so for example, like g y1 to yn equal to just y1 plus y2 plus yn, right? Maybe maximum or whatever. Okay, a certain fashion, right? Maybe just the minimum of each dimension or whatever. If you talk about multi-dimension, right, high dimension, you have a multivariate case. But say if for a simple case, you can think just you add up them all together, right? So it will be say a sufficient statistic for theta if okay you know u, okay, if you only know u, okay, and basically like the distribution of y1 to yn given u will not depend on theta. So what does it mean here? Basically, like if you already know u, okay, then basically if you know the individual y1 to yn, it won't help anymore. Okay, so u should be enough, should be sufficient. Okay, all the information to study theta are already included in u. Okay, so as long as you have the u, you don't need to look at the individual y1 to yn. Okay, so basically like here again we have a intuitive here. All information our data set contains about theta is wrapped in a single statistic u. Okay, so now you just need a single statistic like that. Okay, so this is the idea of sufficiency. Okay, so for example like here, okay, if you consider like n IID observation from x1 to xn, okay, they finally Bernoulli p, right? So saying like the voting, right? So x1 to xn just they vote for the new candidate, right? Candidate. We follow Bernoulli p here. So here, like if we know the value of y equal to sigma xi, right? So the question here is that can we gain any further information about p by look at the individual value x1 to xn? Okay. And if the answer is no, and then basically this will be a sufficient study for p. Okay. So say like one person will know the individual information, right? Another person just know the summation. So whether the person know the individual, they have the advantage compared to the person just know the summation in terms of estimating p, right? Under this model scheme, model scheme. So if they just get basically the same, right? If you look at individual, you just get the same amount of information as the person look at the summation, right? And then basically at the time we have sufficient statistics. Okay, so this is a very powerful idea. We learned the tool to verify sufficient statistics, but basically more or less again, the idea is that you find a way to wrap all the observation. Okay, you wrap. I don't know. You do the max, you do the mean, you do the summation, or whatever. Okay, but that wrapping it includes everything about the thing you want to do study, right? So again, the goal of statistics or data science or whatever, okay, you just estimate some underlying truth, right? And use that to predict something, right? This is the whole nature of the data science or statistics, right? You have something, you model, right? With some underlying truth, no one know, right? And you collect data, and from data, you try to learn that, right? And you use that to make some prediction or inference, whatever, right? And here, like instead of you look at the individual observation, now you try to find whether you can look at something else instead. So in this case, you look at summation. Okay, you look at summation, and if again, if you look at the summation, and it should be enough for you to study the p, and then at that time, we call it a sufficient study for p. Okay. We will have a tool to do this thing, okay, to verify whether we have enough or not in a couple of next slides. But before we go for that, let's look at a very important concept, okay, we call a likelihood function. So here, like, if you have like y1 to yn, basically the sample observation taken from y1 to yn. Okay, so let's say basically you have like the random variable y1 to yn, right? And then for a sample, you will observe the value, right? The value. So for example, here you talk about the height of the US people, right? And then y1 can be modeled by y1 to yn, right? And I just go outside and collect data from maybe 100 people, right? So I have small y1 to yn is the height, right? Just a sample. And in this case, our random variable is depends on the parameter theta. Okay. If we want to yn discrete, right? So for sure we have like discrete case and we have the continuous case. For discrete case, we have like we saw called the joint probability, right? A joint PMF, right? And for the continuous, you have we call it the density function, right? But often this is how we call them, right? So other time basically like for each case we will have a function we call the likelihood function, okay? And the likelihood function here for it can be written, okay? So here for discrete case, we because we have like n independent observation, right? So basically the likelihood function for a discrete case is just the mass function as each point, p1, y1 given theta, y2 to yn given theta. And for continuous case, we just write as a f, right? The density function, fy1 to given theta to fyn given theta, okay? So basically like after you model, right? You model your random variable and you collect your data and you can always write out the likelihood function, okay? You can always write out likelihood function as long as you have the random variable exists, okay? Okay. So and sometimes people they also use notation by just L theta for short, okay? And again, a typical practice, people also work on, instead of work on L theta, they work on with a log L theta, okay? So you see those things many times from now on, okay? But here just some preliminary notation, okay, for the likelihood function. And this is a very important tool, okay? Because as long as you can model your random variable, a random phenomenon by some say function, right? Maybe some specific random variable or some function, right? Under some nature, and then you can write out this likelihood function, okay? Likelihood function, okay? So let's look at an example here, and so you see how you can write out likelihood function, okay? And we will learn a lot from this likelihood function here to estimate the theta here, okay? This is one very important method. But first of all, let's just try to get familiar with this concept, right? The likelihood function, okay? So here, like we talk about like hybrid tree rows, okay? So a biologist study in the hybrid tree row site in a controlled greenhouse environment, okay? So he modeled, okay, the row's diameter size at a normal distribution with mean mu and a standard deviation sigma, okay? And basically like from a sample of 3 roses, right? He see that the diameters are 7 centimeter, 9 and 12, okay? So what's the likelihood function? So the first question, can we write out the likelihood function if we model the rose diameter in with a normal distribution with mean mu and standard deviation sigma, okay? And then like the follow-up question would be like any idea to estimate the mu sigma, right? But first, before we talk about that, just let's see how can if we model in such a way, right? And how can we write out the likelihood function, okay? So say today is March 3, March 3rd. Okay. So here you should notice that because he tried to model, right? the rows diameter size as a normal distribution with mean mu and standard sigma, right? So basically like the diameter, maybe we call y1 to y2 to y3, right? If you follow, it should be IID, right? We always model by IID. The y with a normal with mean mu and the standard sigma, okay, sigma. So which mean what does it mean here is that if you recall the PDF property density function, right, of y, which is follow normal, is like basically f of y equal to, this is a common thing, right? Exponential y subtract mu square by 2 sigma square, okay? So this is the PDF of the normal distribution with mu and standard sigma, okay? So now because the question here that I write the likelihood function, right? For this case, right? Where you have like 3 observations, right? So here we have a continuous distribution case. So basically our likelihood function will be in this fashion, okay? Fy1 given theta, Fy2 and Fyn, okay? Given theta will be Fy1 given theta. So in this case, yeah, theta will be mu and sigma, right? It's just a 2-dimension case. Fy2 given theta and Fy3 given theta, okay? Know that in this case, in this example, your theta is equal to mu sigma, okay? Mu sigma. In a 2-dimension random variable, okay? So basically now, this is the likelihood function here is that, okay? So if you know the theta, right, for given theta, you can get the likelihood like this. So so now like to find Fy1 theta, you just plug in, okay? And remember your y1 here is 7, okay? Y2 here is 9 and Y3 12, okay? And also note and your Y1, okay, is 7. Y2 is 9 and Y3, which is observation, okay? The observation you got 12, right? 12. So now you just plug in, right? Plug in. So plug in here. So basically in this case, L Y1 to Y3, right? So in this case, you have just Y2, Y3. Y3, even theta, which is mu sigma. Okay, I can write here at this fashion as well. So will be 1 sigma 2 pi, right? Exponential of Y1, right? Y1. So maybe I just make it slow first, okay? And then from after that, we can move a little bit faster. So this is Y1, right? This is Fy1 given theta. And similarly, you can also get a Y2, right? 1 sigma 2 pi, right? 2 pi. Exponential Y2 subtract the mu square by 2 sigma square. And the last guy will be 1 sigma 2 pi, okay? Exponential Y3 subtract mu square by 2 sigma square, okay? So three of them, okay? And because of that, right, you now just collect all the term. So you have your likelihood function now. You have the 1 sigma by square root of 2 pi, the same, right, for 3 terms. So just like 1 sigma by 3, right? And exponential, you just collect all of them, right? The product will be the summation, right? exponential of y1 subtract mu square plus, right, y2 subtract mu square plus y3 subtract mu square by 2 sigma square, right? 2 sigma square. Okay. So what next now? What the next step? Do this clear? So what the next step? Are we done here? Sorry, what did you say? So what? So my question is, what's the next step here? Are we done here? So our job is to write out the likelihood function, right? For this example, right? So are we done here? We need to do something in more. Should we stop here? We need to do more. You get my question? So you think we're done here? But what next? How do you simplify that? You mean like yeah, extract them out? Maybe you can do that for sure. Yeah, often typically people will do that. But here, maybe my point here that one more thing important is that like you didn't use your data yet, right? Now you just plug in your data, just what y1, y2, y3, right? So in this case, you can think that y1 is 7, y2 is 9, and y3 is 12. So basically now we just replace them, right? So it will be negative here. Just 1 subtract mu, right? 7, I'm sorry, 7 subtract mu square plus 9 subtract mu square, right? Plus 12 subtract mu square, right? I just use a curly bracket. Okay. And as William just said, right? After we plug in, and now we can also do a little bit further, right? Process that, right? Sigma 2 pi to a 3 exponential of if you just merge them together, this is what you should expect to get. Okay, it will be 274 subtract 56 mu and plus 3 mu square. Okay, plus 3 mu square. Okay, so this is your likelihood function. Okay, 1 divided by sigma. Okay, square root of 2 pi, right? To the 3 exponential of this much. Okay, so this is your likelihood function. So for the given data 7, right? So this is a likelihood function. Okay, likelihood function for the observed data. Okay, observed data. Y1 equals 7, Y2 equals 9, and Y3 equals 12. Okay. So if you observe different data, the likelihood function will change, right? It will change depending on what you observe. Okay. Clear here? Good. So here, the question here, any idea on estimating mu theta? Okay. So basically again, right? Our job is that we try to estimate the mu and theta, right? It's always the goal, right? Always the goal. What is the underlying truth? And this is why you go and collect data, right? What's the underlying truth? Given the diameter size of this zeros, right? Hybrid zeros, right? So anyone has any idea to estimate mu and theta here? Think about it. So we have a function of mu and theta, right? We call the likelihood function, right? How likely it be, right? So basically, in this case, to estimate mu and theta, right, is a typical job, typical requirement we need to do. So one very powerful technique here is that, when you look at the likelihood, okay, based on the data you observe, right, you try to find the parameter mu and theta sigma, which maximize this likelihood function. Okay. So basically, for a given data set, right, what's the value of mu and sigma can help me, okay, can explain the best for the data I observe. So if I can find the mu and sigma, that can maximize the function, right? Maximize the function. So basically, like it tells us, like for this observed data, it explains the model best, right? With that parameter we can find, right? So basically, like this, we will learn that technique in the section 7 of this chapter. Okay, but basically here I just want to show you why the likelihood function is important. Okay, so always, when you have the random variable, you have to observe, right? And if you can model it by some distribution, right? A typical practice is that you have to write a likelihood function, and from that, you can use the observed data to estimate the model parameter, okay, by trying to maximize the likelihood function, okay, and we call that the maximum likelihood estimator. But it will be in a couple of next class, okay. But basically, here's just the idea is that to estimate the mu and sigma, okay. So basically, like to estimate, okay, to estimate mu sigma, okay. We find, basically we will find, okay, we find mu and sigma, okay, thus maximize, okay, maximize the likelihood function, okay, the likelihood function. Right. So for the given data, okay, this mu and sigma will make that data has the most sense, right? Which is make them likelihood is the highest, Okay, this can occur. Clear here? Okay. So basically, this is one very powerful tool. Okay, but first, in order to access this kind of thing, you need to be able to write out the likelihood function. Okay, likelihood function. So again, another example here. An environmental scientist, okay, study the presence of lead in water at a region. Okay, he tests whether water in certain areas contain contaminate with lead or not. Okay. So assume that the property of lead contamination in the same across all the regions, and he used Bernoulli random variable to model the presence of lead of a sample, and want to estimate the property P. Okay, that a water sample it can contaminate with lead or not, or lead, right? And observe data from 4 different samples as 1, 0, 0, 0. Okay, write down the likelihood function. Okay, so this is another example. Let's see. So how about you write this likelihood? Okay, Okay, I give you a hint and you write out likelihood here. Okay, insert here. So basically, here you have like four right? Y1, Y3, and Y4, right? It follow Y with Bernoulli B, okay? Bernoulli B. And you observe that Y1 equal 1, okay, which is like lead contaminated. Y2 equal 0, Y3 equal 0, and Y4 equal 0, right? So your job here is that you have a discrete case, but more or less it's just pretty much the same, right? Find the L, Y1, Y2, Y3, Y4, given theta, right? In this case will be P, okay, I just write down thing here, given theta, Y3, given theta. Okay, and you recall that, okay, recall that. If Y follow Bernoulli P, right? And the B of Y will be like just a P to the Y, right? So Y here equal to 0, 1, right? And Y minus P to the 1 minus Y, right? So this is the PDF function for the here your Y belong to 0 and 1, okay? Okay, so now your task, okay? Let's do the quiz here. Find the L theta, okay? 2, Y3, Y4. Given theta, I'm sorry, given theta. So in this case, yeah, theta B, right? B. Okay, just write out, okay.